Welcome to GWA Physics, and here's the second problem that I was going to go over for the review for the test for tomorrow. So this is the last problem on the review sheet, number 5, or maybe number 6 down at the bottom. So here's a roller coaster that goes all the way through a loop-the-loop, and it comes back up this hill, goes across some friction, and runs into a spring. Again, like I said on the previous problem, the conservation of energy says that once we can solve for the total energy at the top of the first hill, the amount of energy at every single place will be equal to that total energy. It will be a sum of energies that we can account for. So let's look at this first. They said, what was the work done to get this block from here up to the top? Well, work done over here is a force times a distance. So you've got a 2 kilogram weight or mass, and so the force there is going to be 20 newtons, and the distance that we're raising it is 5 meters. So you can see that the work done is going to be 100 joules. Or 100 Newton meters. Newton meters and joules are the same thing. So then when we get up here, the potential energy is equal to mgh. And again, we've got 2 times 10 times 5, which is 100 joules. So that's showing us that work energy theorem, which says that the work done on the object will be equal to the change in its energy. And it went from having 0 amount of potential energy to having 100 as a result of raising it 5 meters off the ground. Now, that means that at this spot right here, there's 100 joules. Right here at this spot, there's 100 joules. Right here, there's 100 joules. Right here, there's 100 joules, and so on. And I said in class, solve for the potential energy first, and the rest of those energies, it'll be easy. So we've got 2 times 10 times 3. So we've got the potential energy is equal to 60. Well, that means that the kinetic energy must be equal to 40. Here, you've got the box only 1 meter above the ground, so it's going to be 2 times 10 times 1. So the potential energy right here is equal to 20. So that means that the kinetic energy is equal to 80. Right here, the height is 0, so the potential energy is equal to 0. So that means that the kinetic energy right here is equal to 100 joules. And you should remember that we said the energy at the top of the hill will be equal to the energy at the bottom of the hill, and it's made its way all the way to the bottom without any friction, so 100 joules at the top is equal to 100 joules at the bottom. Now, if we work our way back over to here, we've got 2 times 20 is potential energy of 40 joules here, which means that the kinetic energy should be 60. Then we're going to lose some energy due to friction, which will give us the remaining amount of kinetic energy here. We'll work this part at the very end. Let's go back over here and see what we've got. It says here that they wanted to know what the velocity was at this spot. Well, the velocity comes from the kinetic energy. So you've got 40 joules is equal to 1/2 of mv squared, and the mass is 2. So 1/2 of 2 is 1, so really it's just that 40 is equal to v squared. We take the square root of 40, and the velocity is 6.32, and that's meters per second. Down here, the same thing. They're interested in the velocity. And since all the energy is going to be kinetic, we've got 100 joules is equal to 1/2 of mv squared, and this is a 2. So we're going to have v squared is equal to 100. So v is going to be 10 meters per second because the square root of 100 is 10. Now let's look at this sheet right quick and get a couple more pieces of information. It says that the coefficient of friction right here is equal to 0.50. And it says that the distance across right here is 2 meters. In the previous problem, we said that the work done by friction is the coefficient of friction times the normal force times the distance. So we've got 0.50 here. It's a 2 kilogram mass, so the normal force is 20, and the distance is 2. So 0.5 times 20 is 10, times 2 would make it 20 joules of energy that was lost. So if we have 60 joules here, and we lose 20, then the kinetic energy right here before it runs into the spring should be 40 joules. Now, we're interested in this spring and how much it's going to compress. Let's write that right here. The potential energy of the spring is equal to 1/2 kx squared. Well, the potential energy in the spring will be 40 joules once this energy has been transferred to the spring, and half of 280 is 140 x squared. So we divide this side by 140, divide this side by 140, and when we get our answer, then we're going to take the square root to solve for x. The x value here comes out to 0.53 meters. Now I hope you can see all of that on the board. I did it pretty quick, but all the calculations are there. If you have any questions, you come in before school tomorrow, and hope you have a great evening. I hope you study hard. Thanks.